Let's begin. Great. And a warm welcome to everyone this evening. Matt reported minutes ago that there are 225 of you who had signed up for the session, so we're very excited about that. And we know there's huge interest in this particular topic. We have, as I mentioned just a moment ago, to those who got into through the waiting room early, that we have three excellent speakers that we'll introduce to you in turn in a few moments. But just to give you a little bit of background, and as Matt said, do put questions in the chat box. And if you are not a Harvard Village resident, please tell us where you're from in the chat box. It's nice to know how far our publicity reached. In our last session, we had people as far away as Ottawa and Windsor. Just briefly, for those who aren't of the Harvard Village, the NetZero committee, a carbon committee actually, officially as it's known, is a dozen individuals who have been planning for a 10-year project for the last year and a half. We've had a couple of sessions like this, the recordings of which are available still on the harvardvillage.com website. But the 10-year project has two sides to it. One is to see if it's possible for a single neighborhood, in this case, the Harvard Village, to actually achieve the Paris climate targets of a 50% reduction in greenhouse gas emissions by the year 2030. And we more broadly see our project as having two sides. One is to put on educational sessions like this one, and there'll be many more like it. And secondly, to organize bulk purchases of air source heat pumps, electric bikes, induction cooking stoves, exterior retrofits, maybe geothermal. We've got a fair list. And for that reason, in part for that reason, we've also reached out to close to 75 residents associations, of which a third said, absolutely, count us in. We will happily distribute that information, because any good bulk purchase is going to be more valuable with more participants. So those are the two sides, and you can read more about that if you go to harvardvillage.com and click the NetZero button. We'll give you lots more information than you ever wanted to know about our project. But tonight we're turning our attention to air source heat pumps, and it's I think there was no hesitation in our committee to choose this as our first sort of a focused webinar on a particular technology or a particular service that can drive carbon reduction. And the reason is that there is no singular action one can take to reduce the carbon footprint of one's home than by ditching a natural gas furnace and going all electric with an air source heat pump. And so I'm really excited to have three people tonight who can really help address that topic. And I'm going to introduce Steve Cornelius first. He is the business development representative with Mitsubishi Electric. He has 10 years of experience in the HVAC industry, which stands for heating, ventilation, and cooling, and for the last 3 years, he's been with Mitsubishi Electric. He'll introduce his sidekick, Chris DeRoche, who's going to say a few words at the tail end of Steve's presentation, and afterwards, I'll introduce you to Trish Long from Goldfinch Energy. Steve, would you like to proceed and screen share and bring up your presentation for us, please?
For sure. Okay. Okay, so it should be up. Can everyone see the title screen?
Yes.
Okay. Okay, welcome, Harvard Village Association members and residents of Toronto. Let me start off tonight by saying that I'm a professional, but I'm not a professional speaker. So please don't judge me by my eloquence, but by the content of my presentation. I've been in, as Tim said, I've been in the construction industry in various roles for 10 years, and the last 3 have been with Mitsubishi. When I was first introduced to heat pump technology back when I was in school, I didn't put much thought into it. And over time, as I've delved deeper into heat pumps and what they can do, it's become obvious that they're a fantastic solution to the status quo. Joining me today will be Chris DeRoche, who's our applied product manager and is distinctively knowledgeable about hydronics and will speak to the residential applications. This image is something I like to show. It's what people might think of our dystopian future, what it might look like, but I can assure you that it won't come to this. I spent some time in Europe just this fall, and they beautifully integrated into heat pumps. They've been using them for years, and it melds into their beautiful facades of their buildings. So this is not our future. So today I'll cover a little bit about Mitsubishi, the evolution of the heat pumps, emissions and energy efficiency, operational costs, product applications, some residential applications, and then Chris again will deal with hydronic solutions for those of you who have hydronic heating. So why are we here today? Is it because of the Pan-Canadian framework on clean growth and climate change? Is it because we're the 5th highest CO2 emitters per capita? For some of you, maybe, but I assume it's because we all have some interest in living in better, more efficient spaces. My hope today is to convince you all that heat pumps are effective, efficient, and economical way to thermally condition a home. Now, if you seek out information, there are countless independent studies by government agencies and NGOs about the energy efficiency of heat pumps. So this really shouldn't be in question. The real question is, does it make sense to use this technology in place of conventional systems? Now, because Canada is a very natural resource rich country, it makes sense that we've been dominated by fossil fuels to heat our homes. Now, the rest of the world, which isn't as fortunate, have looked to alternative measures, and they've never really looked back. So there are two pervasive considerations that plague the wider Canadian adoption. So it's operating costs and operation at winter design temperature. And today I'm hoping to enlighten you to the fact that cold climate systems do make sense. So we call ourselves MESCA, which is Mitsubishi Electric Sales Canada, and we are the HVAC division. We're a Canadian subsidiary of Mitsubishi Electric from Japan, and we were established in 1979. We're highly involved in sustainable initiatives, and we're members of the CAGVC, which is Canadian Green Buildings Council, Canadian Home Builders Association, NetZero Council, Active House Canada, Passive Buildings Canada, and Interquality, and probably a few other organizations. But basically, we try to get involved with any firms and organizations that are looking to do more sustainable development or engineering projects to build a better future for Canada. So adoption in Canada, it's been really slow, but has consistently gained year over year. And even with the past 2 years of the pandemic, we've seen the largest uptake in the industry thus far. And that's, again, across the whole heat pump industry in Canada. Nationwide, around 2.5% of homes use heat pumps. And driving this adoption is the Building Science and Energy Advisor. We're finally looking at homes as a system and taking into account appropriately sized systems, air leakage rates, indoor air quality, and energy efficiency. What is a heat pump? The heat pump is a mechanical device that uses a refrigerant to transfer heat from one place to another. It uses a similar refrigeration cycle found in your refrigerator or in your air conditioner, but it can also reverse its cycle. A heat pump provides heating and cooling generally. There are cooling only systems. The advantage of the heat pump is that it delivers more energy than it consumes. And that's because it doesn't use the electricity to create heat. It uses the electricity to run the systems, the board, the fan, the compressor. And it's more energy efficient than any heating or cooling appliance. And the main point is heat pumps are not electric heaters. Now, heat pumps aren't new. Some people are just hearing about them now. Most people don't even know what they are, but they were created over 150 years ago. And as with all appliances, the technology has continued to advance. So the majority of the world's population does need cold climate systems. The Americans to the south of us have the majority of their population in their southern regions, so they're not too concerned about cold climate systems. Mitsubishi Canada has been a leader in the Canadian market, and we saw a need for the cold climate development when the business was first established. And so we've led the development to where the industry is today. So the image you're seeing here is a schematic drawing of a heat pump system. Essentially, you have two heat exchangers, and one we'll call the evaporator and one we call the condenser, but these are interchangeable as they do similar functions. A compressor pressurizes the refrigerant from a low temp, low pressure vapor to a high pressure superheated vapor. It then passes through a condenser where it gives off this heat and becomes a cooled liquid. Then it goes through the expansion valve where pressure abruptly drops, causing flash evaporation. And of course, when something is evaporating, it absorbs heat. So it absorbs heat from the air going across the evaporator. Now, because refrigerant changes state at negative 25 C at atmospheric pressure, by decreasing the pressure, we can cause vaporization or evaporation at very low temperatures, and thus absorb heat energy from the very cold outside air. Now, when we talk about energy efficiency of a heat pump, there's usually reference to something called the COP. This is the ratio of the energy consumed to the energy delivered. So looking at conventional systems like electric resistance heaters, just for an example, they have a COP of 1. And what that means is that if you have 1 kilowatt of energy going in, you're going to get 1 kilowatt of heat out. And so that's 100% efficiency. Now, if you're using a natural gas furnace, which majority of people are, you'll see numbers like 95% efficient. So that would be a COP of 0.95, because not all of the heat is going to be, not all of the energy of the natural gas is going to be transferred into heat. You're going to lose some to light, and you're going to lose some just to gases escaping. Now, oil and propane are even less efficient. Heat pumps produce numbers, COP numbers, up to 5, depending on the outdoor air temperature. And so you say, how is this possible? Heat pumps do not use the electricity they consume to create the heat. It simply runs the components. And so as the temperature warms, the efficiency is greater. But also as it cools, you lower your efficiency. But then you still get a nice average that's going to be anywhere around 2 or maybe 2.5, which is again 2.5 times greater than 100%. When we want to talk about carbon emissions, buildings account for 42% of our carbon emissions in the GTHA. And then we have to look at carbon pricing. In your home, your heating, whether it be for your space heating and your water heating, are going to account for 62% of your energy. And when we look at carbon pricing, the price is going to increase $15 per year up to $170 by 2030. This means that this will double the consumer cost of natural gas. This is something that we all need to look at and take into account. Right now, with gas prices being extremely low, when you're looking at traditional heating versus heating with a heat pump, they're very close. They're very close, and I'll talk a little bit about this later. But then once the gas prices, the carbon pricing starts increasing the cost of gas, then it's going to be a no-brainer business case for people to start heating with heat pumps. Now, talking about more about efficiency, looking at the efficiency of moving thermal energy. Refrigerant is the top. When you look at the size difference of the conduits, you can see the space savings you get, first of all, when you're moving air versus moving water versus moving refrigerant. But refrigerant still has the highest capacity for transferring thermal energy from one space to another. And so when we're looking at this is only for 35 tons. So if we have, sorry, not 35 tons, 3.5 tons. If we're looking at 3.5 tons of thermal energy, you would need a 12-inch diameter duct. You would need a 2.5-inch water pipe, but you'd only need a 1 3/8-inch refrigerant pipe. Here we're looking at an efficiency curve for a 3-ton system, which is 36,000 BTU. And it's being compared to conventional heating systems. Now, as I mentioned before, electrical resistance heat is 100. So it's at 1. So that's our blue line at the bottom, or our blue line down below. And the red line is your heat pump. And you can see, you know, at -30, you're still above 1. You're still at a COP of 1.26, which is 126%. And this slide, I'm speaking to the fact that when you're looking at heat pumps, you really have to look at what their capacities are at the various temperatures. You know, obviously we really care about what is it going to be at the window design temperature. So many manufacturers will suggest that they work down to -25 or -30, but what sort of heat are they putting out at those temperatures? So it so happens with our Mitsubishi product, we guarantee 100% at -15, and we drop down to 80% at -25. And still talking about heat production at low ambient temperatures. When heating Canadian winter design temperatures, it's a challenge for many of the systems to get down to those low temperatures. So as you can see by this graph, a good cold climate system still has a better heat trajectory getting down to low ambient temperatures. Now, comparing a heat pump to a furnace will cycle on and off. Heat pump systems deliver air consistently. There's two-way communication between the thermostat, the indoor unit, and the outdoor unit. Whereas a furnace, you're only getting one-way communication. The thermostat will seek the set point, it'll tell the furnace to turn off, and when it hits that set point, it'll tell it to turn off. With a heat pump system, they detect changes in the room temperature and readjust the compressor speed to provide the appropriate level of heating or cooling. And this is where you really see the the energy cost savings. So you don't have the hard starts and stops where the system is running at max and then it shuts off and then it comes back on. So the image you're seeing here is, you know, the top line is the going for room set temperature. And then the system will cruise along that line, you know, just adjusting the speed and adjusting the heat to reach or to maintain that set point. And then the lower line is the compressor where it turns itself on, but it's a slow startup. And then it reaches a certain level and then it'll get down into a nice low operating condition. And again, this is all about conserving energy. Now, this slide just gives a better visualization of what I'm talking about. And you can see the green car would be an improvement for occupancy comfort because, you know, it goes up nice and slow and then it just cruises along, where the gray car goes up really fast and then it comes down really hard and back up and down. And so these are nice symbols for how the different systems operate. Now, I know we don't live in Ottawa, but we can all agree that Ottawa is colder than here. And the other point is wind chill is not a factor with regards to low ambient temperatures. So this is from 2020 and it's showing the average temp for the year, all the months of the year for Ottawa. And you can see that the average temp low is 14.8. So, you know, on the news, we hear a lot about wind chill, and that's, you know, we hear -20s, -25s, but it may not truly be that temperature. And that's all the system really cares about. The actual dry bulb temperature. And so therefore, if it's only -20, that's well within the operating range of a cold climate system. And here's a quick graph on the cost per megajoule for the various forms of heating. And you can see there's a gap between natural gas and heat pumps. But when you take into account the delivery charges, the service fees, and other charges that come on your gas bill, you could have $20 of usage and have another 40 in fees. And this is where you really get the break even. So if you actually if you cut off your gas service, you could have bills that are lower for your thermal conditioning than if you were just running a standard system with natural gas. Sorry, I'm starting to run short on time, so I'll try to pick it up a little bit. So whether it be for an apartment, a townhouse, or a detached home, a central air handling unit would take the place of a conventional furnace. So it's a vertical box air handler with a coil inside and a fan, and it would hook up to your ductwork just like a furnace does and provide conditioned air through your centrally ducted system. And these come in various sizes from 1.5 tons up to 3.5 tons. Now, this is typically good for homes, well, obviously under 1,200 feet, but up to about 3,000 feet. Above that, your heat load is probably going to be higher, and therefore you'd have to either go to multiple systems and or like a light commercial system, which will give you higher capacity, 5 tons and 6 tons. This slide here, we're talking about the heating capacities at various temperatures. So I have a builder in Ottawa that has a model home where they pulled the gas furnace out and they're replacing with a heat pump, because then they can compare it to another model house that they have that would be exactly the same. So this house is 2,300 square feet. It's built to Energy Star standard. The furnace that was spec'd was 40,000 BTU, and the unit heat loss is 27,500. So you have two options with this. You could go with a 30,000 BTU heat pump with additional heat coil, because at winter design temperature, it's going to be just short at 25,600. So for the few days that it would require the full heat load, you'd probably have to use electric heat coil. But if you went up one size bigger to a 3-ton unit, it would be able to handle the capacity for a house of this size. Now, when we're looking at retrofit multi-level homes, a multi-split system is actually a wise choice for occupancy comfort. When you have a centrally ducted system and a single thermostat, it's hard to satisfy the temperature requirements for level 1 and level 3. So with a multi-split system, you have one outdoor condenser, but you have multiple indoor units. And you can put them on the various levels, in the various spaces, and you can actually control all the zones separately. So you can have anywhere from 2 to 8 zones with a multi-split system. This shows the various models of multi-splits and their outputs. And you happen to have a larger capacity in the multi-splits. They go up to 4 tons. Just for a matter of sharing some information, I was attending a webinar this summer, and a builder actually proposed that it would be cheaper to build a new home with a multi-split system because there would be cost savings with eliminating all the ductwork and the labor associated with sheet metal and drywall. I was very surprised to hear this. This unit here is a ceiling recessed unit. It fits between 16-inch center-on joists. Most interior designers won't object to it. Comes in capacities from 3/4 tons to 1.5 tons, and it's ideal for minimalists. This is a floor-mounted unit, and it's ideal for taking up the space that a radiator might have been in, or possibly a PTAC. Now, the condensers, these are some images of condensers on various homes, and as you can see, they can be mounted almost anywhere. They can put on roofs, balconies, on walls, near windows or doors, because there's no venting challenges, there's no noise issues. These things are very quiet. The one on the left is actually one at the Dexter House in Harvard Village. And then just briefly touch on this. This is a hybrid option for those who aren't quite ready to let go of gas, where you can have a heat pump condenser on the outside with the air handling unit on the inside, and then pair it with a hydronic coil that's fed from either a hot water tank or a tankless water heater. And so you can use a non-cold climate air source heat pump with the coil, so the coil can handle the heavy load, and then for the shoulder seasons, you could run the heat pump. And so you'd still be getting some savings. Obviously, it's not the carbon reduction everyone would want, but it's still a step in the right direction. So this is one of your Harvard Village homes. It's 2,000 square feet, century home with a 3-ton air handling unit. And it also has a 1-ton wall hung unit on the 3rd floor. And I've been told that there's 2 houses in Harvard Village that are heated by air source heat pumps. On the right side, this black mass here is the heat pump air handler, which is hung horizontally because there wasn't enough ceiling space. But it gets it off the floor too, so there's more storage space around it. This one is in High Park. It's a renovation completed in 2020. The total building size is 4,400 square feet. So they actually split this into 3 apartments. The owner of the house lives on 1 floor and then set up 2 other apartments. And so we have a 3.5-ton system and 2 2.5-ton systems for the apartments. And lastly, this is a house that's not in the GTA, it's out in Campbellford, but it's a good example because this is a 1970s bungalow that was previously heated by oil. And the owner decided to switch out for a heat pump. And they haven't had to look back. Their bills are thousands of dollars cheaper. And even with a leaky old home like this, they're still able to satisfy the heat load. So I'll have to end it here and pass it over to my partner, Chris. So hopefully I've left you with some confidence in what a cold climate heat pump system can do. And my wish is to leave a better world for the little people behind it. And if we keep advancing with technology and rebuild more efficiently and more environmentally conscious, then we're doing the right thing by them. So I'll pass it on to Chris.
Thank you, Steve. Can you hear me okay?
I can.
Perfect. Can you see the title slide? Perfect. All right. Thanks, Steve. So again, welcome everyone. Thanks for taking the time to join us today to talk about heat pumps. Before I get started, I just really wanted to take a minute to just give a shout out to everyone involved on the call. It's very reassuring to see how many people are coming out at 7 p.m. on a Tuesday night to learn about heat pumps because you're NetZero champions. I spend a lot of my time doing education and outreach on hydronic heat pumps, which is a different flavor of heat pumps that Steve was talking to. But of course, for any type of HVAC system, there's different solutions depending on the problem. So again, just really encouraging to see all these people interested in new and innovative technologies. And Steve really touched on a lot of topics. I focus more on commercial projects, whereas Steve's more residential, but a lot of the themes are kind of identical between our presentations. So great presentation, Steve. Thanks for talking about air-to-air heat pumps. My section is just to talk a little bit more about air-to-water heat pumps, which is another flavor of heat pumps. And quite simply put, rather than having the heat pump provide refrigerant to an indoor unit that's then conditioning air or heating air, air-to-water heat pumps will actually just have a heat exchanger on them where it's using the heat pump technology, but it's transferring that heat into a stream of water. So I was kind of waiting for it when we started on the presentation, people asking questions about heat pumps. Okay, well, what about my radiator system in my home? So again, different solutions for different problems. So for those of you who do have hydronic systems in your house, so this means maybe fin tube baseboard radiator, large cast iron radiators, or perhaps Infor radiant heating, Infor heating. Those are different ways that we use hydronics, which really just means heat, using water to heat or cool individual spaces. So similar to the heat pump that Steve talked about, we have the vapor compression refrigeration cycle. I won't go into the details, but basically we put power in through a compressor to move heat from one location to another, and the net effect is that we're producing either hot water or chilled water to use in a building. So we can send those to our radiators, we can send those to our domestic hot water tank to make hot water for our domestic tank. And the same metric is going to govern what the efficiency of that system is, which is the coefficient of performance again, which is really just a measurement of the heat output divided by the power input. So when we, bear with me, sorry, here we go. So I guess Steve talked about a lot of different factors, you know, efficiencies of different systems, and I have similar materials, but let's talk about carbon for a second. Ontario, we're very fortunate to have very clean electricity. And natural gas, we have the infrastructure to move it to our buildings. I'm a firm believer in heat pumps, but I also recognize that there's no silver bullet and there's no one size fits all solution to any of our problems. And this means that natural gas is a part of the Canadian economy for years to come, even into a low carbon future. It's not, for me, about using less of it, or sorry, it's not about eliminating it, but it's about using less of it and using heat pumps as much as possible. So we saw in Steve's presentation that, you know, propane, natural gas, these will have a maximum COP of 1. Basically an electric boiler, or an electric furnace, you put 1 unit of energy in, you get 1 unit of heat out. And this is really where heat pumps come into play. And this is similar to what Steve talked, but more on the carbon emission side. But this is looking at the emission intensity. So in Ontario, if we burn if we produce 1 kilowatt hour of electricity, that will produce 31 grams of carbon. And with natural gas, we buy it in cubic meters, but if we convert that to kilowatt hours to measure the energy content of that fuel, providing that same thermal kilowatt hour of electricity compared to an electric resistive heat means that we'll produce 186 grams of carbon. Air to water heat pumps are a little bit different in terms of cold climate capabilities that Steve was talking about, but even with the products that we have available in the Canadian market on the commercial side and some products that we're working on for the residential side, chances are you're not going to be able to use this type of technology down below -20 for residential applications. And on the commercial side, a lot of time that I spend my time speaking about is, even though you can use the commercial heat pumps down to -15, chances are you're not going to, and you're going to use it down to -10. But what we can do is we can compare the emissions of either an electric heat pump, electric resistive heat, or natural gas. And because we have very clean electricity in Ontario, this means that even comparing it to when the heat pump is performing with its worst coefficient of performance, which is typically at very cold temperatures, we're still 2 times cleaner than just using pure electric resistive heat. And if we compare this to a natural gas boiler, even at -10, that's still going to be 12 times less emissions than a natural gas boiler or furnace. And then if we look at a temperature that it was today, it was about 2 degrees today. So today, using an electric heat pump, air to water, as opposed to natural gas, would have been 16 times less emissions per thermal kilowatt hour that you're using it for. So heat pumps make a lot of sense, and they're definitely the future. And there's different ways that we can go about it. But with air to water technologies, not necessarily available from Mitsubishi, but available across all manufacturers, most cases you're going to find equipment that you can use down to -20 Celsius at best. And people really get hung up about this. So the one slide that I wanted to really add in about this was to pull up the weather data, similar to what Steve was showing for Ottawa. This is the 3-year average winter weather data downloaded from Environment Canada for Toronto. And if we look at the 3-year average annual hours, if we look at times where it's been below minus 15 degrees Celsius outside air temperature, on average for the last 3 years, we'll see that there's basically under 2 days where it was colder than minus 15. And it's also important to recognize that we don't have 2 days continuously where it gets that cold. Sometimes we do, but generally it's a few hours here and there in the middle of the night. So maybe between 2 a.m. and 4 a.m. it's getting a little bit colder, but it typically doesn't all happen all the time. And whenever it comes to air to water heat pumps and designing those systems, they're a little bit different, but there are some flexible ways that you can design that into your system to maintain heating at all times, such as buffer tanks, things like that. It's really a topic all of its own, so I'm not going to try to squeeze it into a 15-minute presentation, but 50%, 53% of the total year we spend between minus 10 and plus 10 degrees Celsius outside air, which is good coefficients of performance that you can get from any heat pump. You can get it from an air to water heat pump as well, but it's a little bit of a misconception that people have, because whenever it's the coldest, that's where you need the heat pump the most, but you can still achieve our net zero goals by thinking a little bit differently about problems. And in most cases with air to water heat pump technologies available on the market today, we'll need auxiliary heat in buildings for those few days where it is minus 23 or something like that. But it really shouldn't be seen as a negative. It should be seen as a positive, because you have a redundant heat source in your house. If your heat pump's down for maintenance or service, you have a backup heat source to be able to work well. So when it comes to air to water heat pumps for residential applications, we're working on releasing air to water heat pumps from our Italian factory next year. The product is the IBXN, which is a single phase monoblock heat pump, which basically means that all the refrigerants contained in the unit that goes outside your house. So this can produce chilled water in the summer to provide cooling. So this could be a benefit as well for systems that might have heating only with inflow radiant system. With this type of retrofit, you can eliminate the carbon emissions from your home. And then now, whenever you would normally just maybe open your windows or put in a complete secondary system to provide cooling in the summer, with a monoblock type heat pump, you can provide chilled water to the indoor zone into your home in the summertime as well. And the IBXN is actually a heating, cooling, and domestic hot water packaged unit. And there's not just Mitsubishi providing these, there's other manufacturers in this type of equipment starting to get a lot more popular in Canada. But this is optimized for residential applications. So this can work down to minus 20 degrees outside air temperature. And even down at minus 20 degrees, it can only provide still 45 degrees Celsius supply temperature for your heating system. Nominally, it can do up to 60 degrees, and you want a temperature of 60 degrees or higher to be able to do domestic hot water for Legionella protection. But this is also within the range that you can use that heat to power, to provide heating through cast iron radiators, or fan coil convectors would use a little bit of a lower temperature for. So I think there was a couple questions about older homes in this area of Toronto that would have cast iron radiators in them. So you could use this type of system to still provide very hot water in the wintertime to provide heating. Or if you're doing renovation and you want to put an inflow radiant heating system, you can still do that and operate it at a lower temperature for your inflow radiant system. Whenever you go to make domestic hot water with the heat pump, you can boost the temperature up and make a hotter supply temperature for domestic hot water storage as well. The beauty with this system is that they are typically all-in-one packages, so they will actually just switch between cooling and heating by using a three-way valve. I'm not sure if this is too technical for the crowd today, but you know, in your home, this would be kind of the heat distribution means in the individual zones that you'd have. So convectors, fan coil units, inflow radiant, or perhaps baseboard radiators. And this type of system is just basically using water, and the heat pump's job is just basically to keep adding heat to the water. But what really makes this system unique is that it'll have a three-way valve that you can use in the wintertime, as an example. So if you're making hot water to fill up a buffer tank to be able to meet any loads at any given time, the unit logic can actually switch and control the three-way valve position so that once there's no usage of hot water or the buffer tank's charged up to temperature and it's available for people to use to heat whenever they turn the thermostat on, the internal logic can then say, okay, well, I don't need to really worry about making space heating now, so I'm going to switch over and I'm going to send hot water to the domestic tank to fill that tank temperature back up. And the heat pump systems on the air to water side are getting very sophisticated these days with very advanced controls that will basically be the brains of the entire system. So it's looking at the temperatures in the domestic tank, it's looking at the temperatures of your individual zones, the temperature of your buffer tank, and it's automatically controlling these things, and you can set the priority for the domestic as well. So for example, when a couple people have a shower one after the other in the morning, and then maybe the fourth person goes to have a shower and there's no hot water left for them, that logic can kind of take over and control that to put a priority to the buffer tank. And these types of systems today are also getting sophisticated because the manufacturers are getting smart and recognizing that we need to make control systems better and better. So this can actually control auxiliary heat in the tank. So in summertime, if you want to, in wintertime, if you do need to prioritize space heating, then this unit can just turn on an electric heater in the tank. Or you could integrate it with a natural gas boiler if you already have that infrastructure in your home. But of course, NetZero would be better, so it can control an electric heat in that tank, and that's still meeting your NetZero objective. Similarly, in the summertime, if you're going to use it for cooling, this can actually control operating the unit in heating mode and cooling mode during the summer, so that it's making chilled water to use. You wouldn't send chilled water to your radiant in-floor tubing unless you're modifying that system to work with in-floor cooling, which is a separate topic. But most common way that you would do cooling in a home in a retrofit scenario would be to send that chilled water to a fan coil unit and blow air over it, which we have some options coming up on the next slide. But very generally in the summertime, you can make chilled water. And then once your chilled water tank is satisfied, now the heat pump system says, well, I'm going to go make domestic hot water now. So he'll control and change over the three-way valve and then change the mode of the unit to operate in heating mode. And it's going to make domestic hot water and store that in your domestic tank as well. So they're very innovative systems. So Mitsubishi will have one of these systems being released to the Canadian market next year. It's been a system that's been used in Europe for decades now. We're just working on the certification, but it really shows you where the future is going. We're looking for low carbon solutions. And for those of you who do have hydronic systems in your homes, you probably have natural gas boilers. We're basically burning fossil fuels to make hot water. And if we want alternatives to those systems for NetZero, our only options are electric boilers or electric heat pumps. And because a heat pump will always be more efficient than an electric boiler by a factor equal to the COP, you know where you're going to end up with heat pumps in some shape or form being a part of our HVAC mix in the future. Whenever it comes to residential applications and doing retrofits, for example, if you only have the cast iron radiators and your home wasn't built with any means of cooling and you didn't want to go with a mini split or anything like that, we will be releasing next year as well a line of slim fan coil units that are perfect for residential applications. So these are just 13 centimeters thick, wall mounted, can be mounted behind the wall, vertically, horizontally on the ceiling. Very versatile, but the key point is that it allows you to add cooling functionality to an existing retrofit. And lastly, we'll jump back on the technical side very briefly, but there's always questions about with the conventional temperatures that heat pumps can operate at, can this provide 100% of my heating all the time? And it's hard to give a straight answer because every HVAC system is unique, but very generally you can do two types, if you will. You can size your system so that this is your heat pump curve, similar to what Steve was showing in his slides. But as it gets colder outside with outside air temperature, we have less and less capacity that's available from these types of heat pumps. And if we look at our heating capacity required for your home at the winter, it's basically going to be the most heat's required at the coldest temperature, so minus 15 in this example. And then your heat requirement is going to decrease as it gets warmer outside, because as it gets warmer outside, you have less heat losses from your home. So then it's going to decrease like this. So understanding how the heat pump operates is important. There's a lot of different sizing ways. Here is showing integration with an electric heater so that the heat pump can actually work with an electric heater for those colder temperatures. That's one way to size it. Or the other way is just basically, like I mentioned at the start of the presentation, run the heat pump down to a certain temperature and below that switch over to an auxiliary boiler. keeping in mind there's relatively few hours where the auxiliary boiler works. And this boiler could be electric or natural gas as well. But again, even if it's natural gas, you're using it for very little of the total time. Anyway, that's all I have for today, so thank you.
Chris, thank you very much, and a big thanks to Steve as well. I know that I'm sure glad that we've recorded this presentation, because I know I'm going to go back to run through those technical descriptions myself a few times just to get on top of it. Just before I think we're going to, just two reminders. One is, if you're joining us from outside the Harvard Village, please indicate in the chat what neighborhood, what city you're from. We do have people from as far away as the South Okanagan to the west, and Whitby to the east. We also, if you've joined us after we started, you may not have heard that we're encouraging everybody to put your questions in the chat box, and my sidekick, Matt Hoffman, in a few minutes will start posing questions to our presenters, the third of whom I'm going to introduce now and have her present, and that's Trish Long. Trish has many years of experience in renewable energy, in green buildings, and climate policy and finance. And a couple of years ago, she partnered with Sarah Grant and started a company called Goldfinch Energy, and the purpose of which, or is dedicated to helping Canadians to make smart, clean tech choices. So a big warm welcome to you, Trish, and I will just share with you your observation as we were doing some prep beforehand, that you were excited that Drake had, amongst the participants in tonight's presentation, is Drake, and if it's the real Drake, we know how many heat pumps he'll need in his house. Trish, over to you, please.
Thank you, Tim. Thank you, Tim. Can everybody hear me okay? Good. And thank you, Steve, for your presentation. And next time, I think we want to see that daughter as a cameo. She looks pretty cute. And Chris, nice to meet you. I don't know if we've connected before, but be prepared. I'm going to call you tomorrow with some questions too. Great presentation. Can everybody see my screen? I've got some slides up. Before starting, just wanted to acknowledge I see a number of friendly faces in the crowd. So hello to all of you. And I noticed in the chat that we have somebody from BC on the call. And BC has even better rebates than Ontario. So it's a great time to get a heat pump in BC. And as Tim mentioned, I have a policy background. And while natural gas may be here for a while, Chris, that's not the case for new homes being built in Vancouver as of 2022. When I started Goldfinch, I would always use this to describe what was happening, what I see in the future. And now we're only 5 weeks away. You will not be able to build a new home that's heated with gas for space heating or with hot water or for hot water. They're still allowing stoves because a lot of people are addicted to their gas stoves, but for space heating, it won't be allowed. And then eventually what will happen is people with existing gas for heating and hot water will have emission caps that will come down over time, meaning fines will increase and people will be incented to change. So that's happening, and there are lots of places in the world that are much further ahead than we are: Europe, Asia, California, and now I have the great pleasure of going to at least 3 homes a week where people in Toronto want to get off gas. And sometimes I'm doing an energy audit for them to help them to get rebates, and sometimes I'm doing a 20-year plan for them so they can map it out logically. Most of us can't afford to do everything all at once, but as equipment, whether it be a car or a furnace or a stove, is reaching the end of its natural life, how can you prepare so that when you need to switch, you can do it quickly? So I also wanted to, we do talk about heat pumps when we do our energy audits, but I wanted to talk about the other things that we do as well, or when we want to do a deep energy retrofit to our home. And some of us can do any of these at any time because they're fairly easy. Air sealing is one of those. If you've had an energy audit, they bring in a blade blower door and you test the air tightness of your home and you find all those leaky spots. And the picture at the bottom is my business partner, Sarah, and she's helping one of our clients air seal and insulate their crawl space. And I like this photo because it's a close-up of where the ceiling area is, and that's the header area. And in Harvard Village, I think there are a lot of basements that have uninsulated header spaces. And they leak a lot because that's where all the service comes through your house, whether it be water, air conditioning, gas. So there's a lot of leakage there, and doing something simple like insulating your headers can make your home a lot more comfortable. Another tip, a lot of our clients have done this, it's aero sealing technology. And if you've got a hot cold problem where your basement's too cold in the summer and your second or third floor is too hot at the same time, aero sealing might be just what you need to fix that up. I encourage you, I won't get into it too much here, but I encourage you to look that up. It's also really helpful if you're switching to an air source heat pump. They're more sophisticated than our old gas furnaces, and we need to make sure our ductwork is in good shape when making that switch. If you have a hot cold problem before getting a heat pump, it might be worse after getting the heat pump. So a lot of our clients that switch to heat pumps do that air sealing beforehand, and sometimes they do it afterwards. Next slide. Yes, this is a quick note on the energy efficiency pyramid, which I hate. It's been around for decades, and it's this pyramid showing you have to do this, 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 and it's always the boring stuff that nobody will ever notice. And you have to do all of that before you can do something fun like solar. And I don't agree with that at all. A lot of energy efficiency measures have just resulted in people building bigger and bigger and bigger homes. You know, in my neighborhood, the homes are now 4 times the size of the original homes. And yes, they're more efficient, but a lot of them have 2 furnaces and 2 air conditioners. So, you know, the neat thing about electrifying is that all of a sudden you start to view electricity as precious, and it's not unlimited. And so we stop using electricity for unnecessary wants, and we start focusing on, wow, wouldn't it be neat to get off gas to heat my home? And induction stoves, we got one this year, and it is life-changing. It's better than gas. You know, I challenge any chef on the call to come by and try mine out, and I don't think you'll be disappointed. They're really neat. There are also heat pump hot water heaters, which are an alternative to gas tank and gas on demand. Electric fireplaces look really good these days. They come in sleek, modern models, and you can change the image on it because it's a digital image. It produces heat just like a gas fireplace or a traditional fireplace, but without the carbon emissions. And last but not least, while you know this is going to be an expensive transition, we have the rebates already helping us. I think there are going to be more rebates that help us even more in the coming years. And the federal government has announced interest-free loans up to $40,000 as something that should be, I think we'll be seeing an announcement before the end of the year, and maybe they'll come online in early 2022. Also for people in the city of Toronto, I've heard through the grapevine that the Toronto Help Loan, also for energy efficiency measures, I've heard that the interest rate is going to come down significantly, and that the amount that you can borrow is going up. So we're going to have more help doing these things in our house, and you can do some of the fun ones before you do some of the not as fun ones. slide. Watch out for window marketing. You know, it's so often when I go to somebody's house and they've just moved in and there's a whole bunch of things they need to do, the one thing they want to do most of all is replace the windows. And I know it's really nice to have windows that open nicely and don't cause you problems, but in terms of the energy efficiency of your home, the windows are not what really matter. And these are photos using a thermal camera. And you can see the purple color is where the cold air is transferring to inside the home. And you know, look how much wall there is compared to window. So we use an R value for talking about insulation. If the R value of your windows are a 2 or a 2.5, quite low, if you upgrade them, you're only getting to R4. But in this house, that wall might be an R4 wall, but by insulating it, you can get to R12 or R24, or you can do it in different ways. You can insulate from the inside. You can reclad your house on the outside. And that's what I see a lot of green architects doing, is recladding a house from the exterior, because there can be lots of benefits from putting continuous insulation on the outside. So I know the windows are tempting, but you don't want to move in and do the windows and then 5 years later decide to insulate the outside, because you already paid for your windows to be put in, and you might have to remove them all to do it properly. It's tied to air sealing, and yeah, it gets more complicated. So make a plan and then do the windows at the right point in your plan. And that's it, a quick cover of a number of topics, and I'll turn it back to Tim for Q&A.
Thank you very much, Trish. I for one, had the energy pyramid in my head for 40 years, and you did overturn it when we chatted on Saturday, and only reinforced it this time around. But that was a great overview. I know there's been lots of questions that have been posed already in the chat box, and I think we're going to jump to them, and I'm going to really turn it over to my colleague Matt Hoffman to unmute himself, and he's been perusing the questions and he's going to select them, and I think we'll let our speakers decide who, unless they're directed to a particular speaker, which of them wish to answer, and maybe both or all three will want to answer a question in some cases. But Matt, over to you.
Great, thanks. This was excellent. Thanks for the wonderful presentations. I learned a ton, and I thought I knew something about heat pumps, and so that's great. We have a number of questions. Most of them are fairly technical in nature, but I want to start with there's a number of questions that were about how to use heat pumps in. And I think you talked about multiple floors. And so a number of people had questions about using heat pumps in multiple floors or in multiple spaces. And so we had one question about an apartment, of how to do this an apartment building with 6 units. I'm going to put a couple of these on the table and I think these will mostly be for Stephen and Chris. I have a 6-unit apartment with high efficiency gas furnace that does hot water radiators and on-demand domestic hot water. How would heat pump work in this situation? So a 6-unit. And then we had a couple of questions. One, what if you wanted to use a heat pump just for the 2nd floor? Is something like that possible? And another question saying, I just got a new gas furnace, but I still have multiple relatively chilly areas in my house. Is it possible to use heat pumps for a more targeted application like that? And so a number of questions about can heat pumps be used to deal with the sort of multi levels that houses have and multiple units in an apartment building.
Right. So yeah, let's talk about the apartment, which could be similar to a multi-floor house. So when we look at the multi-split system, I mentioned that they can use 2 to 8 indoor heads. So you're going to have a condenser outside, And then you're going to have up to 8 different heads that you can place anywhere in that house. And so for that 6-plex apartment building, again, you could have a single outdoor unit with 6 indoor units going to the various apartments. They'll all have individual control of their temperature, but they'll have to be in heating or cooling at the same time. So that would be the only mitigating factor there. And then for the domestic hot water, like Trish mentioned, you can do a air source heat pump water tank, and then that could be sent off to the various units, or they could have smaller electric tanks in each apartment building. When you're looking at a home that already has a natural gas system, but say that 3rd floor is really chilly, you could have a very small system, a 1-ton system, which many people do to condition that space. This is something that we try to market to, so that room over the garage, or maybe the attic space, or whatever that case may be, it could have its own system. Again, a small system that will provide heating and cooling for that space, and that's very straightforward.
Great. Now a couple of questions about some of the technical requirements for the house. So one person asked, will a 100 amp service support a heat pump, or do you need to have an electrical upgrade to do it? And another person asked about space requirements, specifically for the IBXN unit, or what's the space that it is required to draw upon. But if you could also speak, I think, to some of the general space requirements for these units, that would be great as well. So electrical upgrade necessary, and space requirements for IBXN and other units that would probably fit in the sort of Harvard Village houses, like the Dexter house.
Yeah, thanks. I'll take that one. Steve, you good? I'll take it.
No, go ahead. Go start with the IBXN.
Okay. So regarding electrical service, like homes in Ontario these days, like even before heat pumps became more mainstream, homes still had air conditioning units. So the electrical capacity is generally not a concern for hooking up an IBXN or even air-to-air heat pump. And with today's inverter compressors, that actually makes the sizing more favorable to work with 100 amp services for buildings. Regarding space constraints, the one thing that you do want to be careful about whenever you're talking about installing air-to-air heat pumps or air-to-water heat pumps is making sure that you have enough clearance space between the coil of the condenser, where you need to suck air through, and the side of the house. So typically manufacturers will provide requirements. I think for the IBXN, for outdoor installations for an obstruction for a wall, I think you want at least 1 meter away from the wall. But there's different sound considerations that you should consult to with your local bylaws regarding the placement of the units. But generally, the technology available today is well below those limits.
And I'll add in for our air source, you only need 6 inches behind the unit, so it can be placed almost right up against the wall. You might have seen in one of the pictures where it was on some L brackets sitting on the side of a building, and then you need 3 feet in front of it. That's it.
All right, now some brass tacks here. A couple of questions about cost. And this goes along with some of the questions that have come up around sort of multiple small units, one big unit, units that are just for specific floors. So a specific question around what would a small 1-floor unit run? Second, what's the cost comparison between doing multiple small units, so like putting them in place for different floors, or one large system? And then in general, questions about maintenance. Like, what are the maintenance costs and what are the lifespan of these units? Because some of, obviously, the costs of switching to heat pump would have to do with how many heat pumps you need over the lifetime of if you stay in a house for multiple decades.
Okay, I guess I'll take this. Don't usually get into pricing because we're the manufacturer. We don't actually sell it to the public. It goes through our distribution network, and then obviously the contractors install it. So I really can't speak too much about price, but with regards to longevity and maintenance, maintenance is really straightforward. Your indoor units are going to have filters on them, air filters. And so depending on how much particles you have in your air, so if you have a lot of pets, then you're going to have a lot of hair. So that's going to clog it up a little bit more. So got to keep on top of that. For the outdoor units, it's debris like leaves, dirt, any of those sort of things. Because again, this system has to be able to pull the air through its through the coil. And so you want to keep that clean. So if it's basically yearly, you want to make sure that it's cleaned out. Usually do it with compressed air. And that's about it. But for longevity, we're talking about 20, 25 years. We have systems that are 25 years old still running. The only issue is that they're running R22 refrigerant versus the current R410.
Did everybody hear that? Steve just promised us 25 years. I'm kidding, Steve. But yeah, no, we do have a few clients that have installed them and they've not had any problems. So we're off to a very good start. But I wanted to jump in on pricing. Working on the retail side, I've seen a fair amount of that now, and there's a full range. We have clients that have a heat pump is basically a fancy air conditioner that also works in reverse. So we all have, most of us have an air conditioner. So most of us already have a heat pump working. And so we have clients that have replaced a traditional air conditioner with a heat pump, and they pair this with their furnace in a hybrid system. And they've done that for $4,000 to $5,000 for the most affordable one, but you can spend more on heat pump in a hybrid situation. You could spend 6 or 7. And then there are centrally ducted heat pumps that if it's doing a good size home, that'll cost you $16,000 or $17,000, maybe $19,000 for a complex install. But it's a little bit different than just buying a furnace or just buying an air conditioner, because you usually don't do those things at the same time. We're used to buying a furnace for $6,000 or an air conditioner for $4,000, but we don't add it all up at the same time. So you kind of have to add up that a heat pump does your heating and it does your cooling. So I know people that have spent $14,000 installing a good quality furnace and a good quality air conditioner at the same time. So then it's more realistic. It's $14,000 to say $18,000 jump for the heat pump, but that's why we've got the $5,000 Greener Homes rebate happening right now. So it brings it down to comparable. The high-end ones are still a little stretched, but they're doable, and there are going to be more and more alternatives on the market as this goes along.
Great. I'll jump in here. Trish, I've got a question for you, kind of going back to your, you overturned the energy pyramid as you described it, and I didn't take advantage of that point you made to sort of ask the next question, which is, if we're overturning the energy pyramid, in other words, if it makes sense to get an air source heat pump now before you've done all the other things, you've super insulated the walls from the outside, you've done all the air sealing, probably that should be done first. But before doing a half dozen other measures to reduce the energy load on your house and then buying the right size air source heat pump, why isn't there a problem of, if you start with the heat pump and then you do all the conservation measures that reduce the load, that you end up with an oversized heat pump?
Yes, good question. Not necessarily. Furnaces come in all sizes. They can be 40,000 BTUs, 50, 80, 100, 120. You just burn more gas faster. But a heat pump is different. A heat pump only comes up to limited sizes. And as Steve talked about, the Mitsubishi being a maximum size of 3.5 tons, which is 42,000 BTUs. So if you have a heating load at your house of 50 or 60 or 70,000 BTUs, your heat pump's going to get you most of the way there, but not all the way there. And Chris talked about the weather data and how few days we have below -15. So on those few days, your backup electric radiant heater built into the heat pump air handler sometimes is going to kick in and make sure that your home is heated to 21 degrees on those 2 or 3 days. So technically that would cost you more on those days than burning gas, but it never adds up too much. And again, I'm talking about modest sized homes, and Harvard Village is the perfect example. There aren't too many monster homes in Harvard Village. And plus there are a number of semi-detached or row houses. So if you're already sharing 2 walls or even 1 long wall, you've got a lower heat load than other people. And what it means is you can put in a heat pump now, and over time, as you insulate the walls and upgrade the attic insulation, finish the basement, your heating cost will come down. But yeah, no, there are certainly cases, and there was a blogger in the US that started out with, he knew he was going to do all those upgrades, but the furnace broke when he first moved in, and he wasn't going to buy a new furnace for the year or 2 it would take to do the upgrades. So he put in the right size heat pump for his finished project and plugged in a couple of space heaters to make it through the year or 2.
Great, thank you.
Excellent. So we have a series of questions about, oh, actually, before I do the question, someone had asked about getting in touch with the HVRA NetZero committee. And I and then I think Ann Stevens also put our website in the chat. And so if you're interested, the website for the HVRA NetZero committee is in the chat, and you can see what we've been up to and get in touch. I had a series of questions about how heat pumps can work with existing systems. So one person asked about, can they work with existing radiant floor heating? How do you know if your existing ductwork is adequate for a heat pump? Someone asked if it can work with an existing ERV unit. I'm looking forward to hearing what an ERV unit is. Or how could it work with retrofitting with a tankless water heater? And so I think that people are really interested in how heat pumps can work with a lot of existing systems that are in houses.
Okay, so I'll take that. So when you're looking at integrating a heat pump with an existing furnace, what you're going to have is a condenser on the outside, and then your indoor unit is going to be a coil, and we call it an A coil. So similar to when you add an air conditioner to a furnace, pretty much the same setup. So that coil is going to be able to provide heating and cooling, and that would be placed inside your furnace, and that would pair up that system. I showed a quick slide on a hydronic hybrid system where the tankless water heater was paired with a hydronic coil that was placed in a air source heat pump air handler. That's the way you can tie those 2 things in. Otherwise, the tankless water heater can just keep doing what it does, supplying you with your domestic hot water. And then as far as in-floor radiant, I think Chris spoke to that with regards to our air to water systems, which are soon to be here. But there are manufacturers that do produce air to water systems that can be integrated into in-floor heating. And with regards to the ERV, that's a energy recovery ventilator. So you may have heard of an HRV, which is a heat recovery ventilator. They're similar products, except the heat recovery ventilator is capturing heat from exhaust air and putting it into fresh air that's being brought into the home. The ERV now can also it does heat transfer as well as humidity transfer. And that's why they call it an energy recovery ventilator.
Most new homes are built with a HRV or an ERV because their air change per hour is under 3. Those of us in older homes have natural ventilation through all the leaky spots in our homes. But if you do start cladding your house on the inside and making it airtight, fresh air exchange is something you need to start adding to your house. So they're more and more common.
Right. We're running down to the end here, but a question about whether a heat pump deals well with sudden temperature fluctuation. So if we get one of those, fronts that come through, like we've had a couple times where, maybe it was 10 degrees one day and it's -10 the next day, or even within a couple of hours, does a heat pump deal well with that?
Yes. So unlike radiant heating, which can adjust quickly, it's a very slow temperature change. When you're dealing with thermal air, then it is a quick change. So the system will detect the change. So obviously you have a leaky house because when that temperature drops outside, the temperature drops inside. If you have a nicely sealed house, you don't see that temperature drop so quick. But if you have a leaky house, then yeah, you'll feel it. But the heat pump will ramp itself up to meet that demand. So it has the ability to adjust its flow and its compressor speed to match whatever is required. So yeah, like say you had the door open all day for whatever reason, it's going to ramp itself up to try to meet what the load is in that home. So there's no issues there.
So just a follow up, and this was actually from me. You gave some really nice technical details and information about sort of what a heat pump does at the low end of the temperature scale. But what does that translate to in terms of, how easy or hard it is to keep your house at, say, 20 degrees? So when you see the drop off when it gets colder and colder, what does that mean for what you're actually feeling in the house during those times?
As long as the system has the capacity to meet the demand in the house, then there should be no change for the resident. It's when it's reaching its limit, if it can't, say it has a maximum capacity of 26,000 BTUs, but your house is, at the coldest would be 32. Obviously there's going to be a gap there, and the indirect temperature won't be where the set point is. And that's where you'd have to have the electric coil or whatever supplementary system you have. But if it's sized to handle the full load of that home, it will supply the heat required down to your coldest days.
And to jump in there and add a bit on auxiliary heat can take different forms. Steve talked about it being in the air handler unit, sitting on top of the heat pump. And so if it is a -25 day and it's, the heat pump is producing less heat, what's important to note is that the coil comes on top, but the heat pump is still working because it's still giving, 1.3 or 1.5% efficiency. So it's cheaper to run than your electric radiant coil on top. There was a question earlier I saw in the chat about a hybrid system and how much gas can that offset. The challenge with a hybrid system is it's set up so that your furnace is at the bottom and the heat pump sits on top, but because of code, they cannot run at the same time. So if the furnace is on, you can't use your heat pump at all. So the gas company really likes the hybrid model because, you get to minus whatever, let's say you get to -2 and then your heat pump shuts off and takes you through the colder months, and then it comes back on as spring is coming. So Matt, as you see the decline there, it just means that you're using more of the radiant heat. So you pair your auxiliary to match the coldest temperature, so you don't get cold. I only have one client that's testing it out this winter without auxiliary heat to see what happens, because you don't exactly know the heat load of your house until you test it.
That would be me, but the rest of my family would really object to that experiment being done in my household.
Right,
Probably.
but your auxiliary could be 3 space heaters the first winter.
Put on a sweater. You'll be fine.
Indoor camping.
That's right. Just a last couple of questions, and then I think we will. I don't want to abuse the generosity of our speakers here. And again, a couple of technical questions. What about humidity management? And this is a very technical one, would the BTU of heat pump for both heating and cooling be the same as an existing AC unit with a SEER of 15? I assume that's an efficiency rating. And is an oversized system a problem? Is efficiency reduced due to frost on pipes or anything like that?
Okay. Yeah, go ahead.
Okay, sure. I guess regarding the question, BTU of a heat pump, comparing that to SEER, those are two different metrics. So SEER is a seasonal energy efficiency ratio. So this takes into account that it's not really, really warm out in air conditioning temperatures for the entire year. If it's 15 degrees Celsius outside, you might still be doing a little bit of cooling in your house. So really in terms of retrofits, you're really just matching the nameplate capacity of the unit outside and then replacing that with something that has equal or better capacity. And then now the next thing to look at is what's the efficiency of the old device versus the new device and compare them. So you're still moving. So for example, if you had a SEER of 15 with an existing unit, you match the capacity and put in a newer system. Like what's the SEER on a Mitsubishi air-to-air system, Steve?
16 and up. So the bigger ones are lower and the smaller ones are higher.
Yeah, so you might be talking anywhere from 16 to 18, and it might not sound like that much of an improvement, but what's 18 divided by 15 is 20% improvement. So that's 20% less cost to operate over the year. So they're kind of two separate thoughts, and I just wanted to make that distinction, but obviously higher efficiency, the better.
Last question on humidity control.
Sorry. Humidity management. Regarding air-to-air heat pumps?
I was hoping we'd get Chris to solve that with an air-to-water heat pump.
Air-to-water heat. So there's a question before on air-to-water heat pumps, and I was also trying to answer some of the questions privately on the chat just to give people answers, but in commercial buildings, we use hydronic cooling in fan coil units to remove heat from the space, but also to dehumidify. And that's why anyone who's ever had like a dehumidifier type unit will generate condensate. And that's actually moisture that's in the air in the space that you're living in, that's removing it. Same concept as a can of Coke that you put on the counter whenever it's warm in your house and you have condensation starting to sweat on it. With air to water heat pumps, you need to use those convective methods to remove heat from it. So it wouldn't really work with a cast iron radiator because that just basically becomes an ice cube and then you have condensate forming on it. So you would need to install another type of system, but that's a little bit less intrusive because you're still able to use the piping and maybe put in a 3-way valve to switch to divert water instead from your cast radiator to a fan coil unit is one way you could do it. Radiant import cooling is also a thing. It's not very popular because it doesn't dehumidify very well and the controls are more complicated to make sure that the floor is always above the dew point in the space, but that's another method that can be used as well.
And on the air-to-air heat pump side, you should have better humidity control because most of our air conditioners are not very smart and they have 1, maybe 2 speeds. And so it's either on or off and it's sized for that hottest day of the year. So most of the time it's coming on for a relatively short time and then turning off again. So there's less time for a large volume of air to pass back through the air handler where the dehumidification happens. Whereas the new heat pumps have a fully modulating blower So it can move the air more slowly, getting it to run more volume of air running by and removing humidity in the summer. So there's the advantage there. And then there's also an advantage in the winter, because gas, you can't, it burns at there's a minimum temperature it burns at, and that tends to remove humidity from the air. Whereas a heat pump is more steady, warm heating for more often. You remember Steve's drawing of the car going like this, and the heat pump going like this, because it's not hot air, or some people call it for forced air, scorched air. Because it's not so hot, it's not drying out the air in the first place. You still may want a humidifier so that it's always controlled, but it's not needed nearly as much as with a gas appliance.
Great. Well, I will jump back in please join me virtually in as best in our muted states in a big warm thanks to Trish Long from Goldfinch Energy, to Steve Cornelius and Chris DeRoche from Mitsubishi Electric for really detailed answers to which I think really revealed how many options there are for the variety of houses in downtown neighborhoods. I think it was a very rich presentation. I also want to thank Matt Hoffman for kind of keeping the tech side in shape and assessing which questions to ask our speakers. So big thanks to you, Matt. Please, all of you who, again, if you found this useful, do share the details with your friends. Ask them to sign up for our mailing list at harvardvillage.com, in the NetZero main page. There's a link at the bottom so that they can hear about forthcoming webinars, as you will, and bulk buys that we'll be organizing in the months and years ahead.
Tim, before you leave, can I just give a year's financial data on installing a heat pump?
This is Sue Dexter, who has
You
one.
betcha. You betcha. And thanks to Trish and Steve. I mean, and to Transform TO for all the work that was done. The interesting thing about tonight is that if you installed a gas furnace, you would never phone Enbridge and say, now, how does it exactly work? And where is the condenser and where is the this and that? It's new technology. And what happens is it gets put in your house and you've got a thermostat and you turn it to 68 degrees or whatever you want. The financials are this. In the winter, it was slightly more costly, like $144 more expensive to run the heat pump than my old gas furnace. In the summer, I saved $40 on cooling because it's a better cooler and I had a better result on cooling my house. So the net at the present tax on carbon was $100. So it cost me probably less than $10 a month to get rid of 60 or 80%, whatever it is, of my carbon emissions. And I can tell you that's a great feeling. So that's my report. But thanks both to Trish and to Steve. And I have one last thing to get rid of, and that's the on-demand hot water heater. And then I am off gas.
Thanks, Sue, and thanks, everybody. We'll look forward to next time, and have a great rest of the evening.
Thank you, Tim, for hosting. Thank you, Matt.
Thanks,
too.
all. Thanks, Tim.
Good night,
Nice
everyone. Thanks for having us.
Nice
Thanks,
to meet
Tim.
you, Chris.
Appreciate it.